Welcome to Two Beans in a Pod.
Hello, everyone.
So we're seeing something pretty remarkable right now. A real parade of icy visitors, comets, streaking through the inner solar system. Some really spectacular green ones, actually. Notably, there's C2025K1 Atlas, and it's making a pretty perilous close approach to the sun.
Right, that one's cutting it close.
Yeah, but the object that's really, ignited a lot of curiosity, maybe even controversy, is 3A Atlas. That's the recent interstellar visitor, the one first spotted by the European Space Agency's Mars orbiters.
The Interstellar one. Always exciting.
Exactly. And this whole influx, this group of highly active, sometimes volatile comets, it naturally brings up a pretty fundamental question, doesn't it, about how things work in the solar system.
Which is?
Well, can the close approach, the intense activity, the sheer mass loss from these comets, especially this unique Atlas group, could it actually physically trigger or maybe just influence large-scale solar events? Like a coronal mass ejection, a CME?
Okay. The trigger question.
Or is it just coincidence? Is the timing purely chance following the established scientific consensus?
Right. That's the core issue we're diving into today.
It is. And I'll be arguing that the unique nature of these comets, especially the interstellar one, 3A Atlas, it's energetic, it's not from here, that this warrants a really rigorous look into a potential, maybe non-conventional causal link. We shouldn't just dismiss it.
Okay, and I'll be upholding, the established consensus. Solar physics is pretty clear that these big solar events, CMEs, they're magnetically driven. They're internal to the sun. And, frankly, coincidence remains the only scientifically supportable explanation for any apparent link we see.
Okay. Well, I see why you rely on the historical data and the standard model. But let me offer a different perspective here. One that really hinges on the composition and the origin of these specific objects. Because the unique characteristics of 3 Atlas and the extreme closeness of C2025K1 Atlas, I think they demand that we challenge that easy assumption of simple coincidence. We're just not dealing with a typical icy body that formed out in the Kuiper Belt. The distinction, I think, between a standard run-of-the-mill comet and an interstellar interloper like 3A Atlas, it's critical. This thing comes from outside our solar system. It could be carrying matter that's, maybe 3 billion years older than our own sun, and it's showing behavior we didn't really predict. The evidence suggests it's just far more volatile than our native comets.
More volatile how, specifically?
Well, for instance, the Swift Observatory studies, they quantified this volatility. They detected massive water loss, described, I think the quote was, like a fire hose running at full blast. That's roughly 40 kilograms per second. And get this was happening when it was still incredibly far out, nearly 3 times farther from the sun than Earth is.
Okay, that is unusual activity for that distance.
Right? So that unexpected high-velocity mass loss, you couple that with C2025K1 Atlas, potentially making this death dive towards perihelion. You're injecting massive amounts of volatile, unique matter directly into the chaotic magnetic environment of the solar corona. To just dismiss that input as totally irrelevant, no matter how extreme the timing or proximity, it just feels like, scientific conservatism may be blocking some essential inquiry.
That's a compelling argument, definitely, based on the novelty of the material. But I would frame it differently. When you propose a causal connection like this, the burden of proof it rests entirely on presenting a physically plausible mechanism. And right now, established solar physics, it dictates that these events, the comet's passage and the CME, they are entirely separate phenomena. Novelty alone doesn't grant causality,
But the mechanism might be subtle.
Well, let's talk about that injection of mass you mentioned. We need to look at what actually drives the event we're discussing, a coronal mass ejection, a CME. These things are fundamentally internal, they're magnetically driven. It's the result of these immense flux ropes of magnetic field lines twisting up, storing huge amounts of energy, then breaking and reconnecting within the sun's atmosphere. Solar physicists, the experts in this, they've been very clear. They don't know how a comet could spur such a process. The scale disparity is it's overwhelming. I mean, think about the comets we often see, the ones observed by missions like SOHO, at the Solar and Heliospheric Observatory. Many of them graze the sun, right? But their cores are typically tiny, maybe 330 feet, 100 meters wide at most. The sun, on the other hand, is immense. It's 865,000 miles across. The prevailing expert view, and this is supported by rigorous analysis of past sun-grazing events, it concludes that these historical coincidences, they can all be better explained by simple statistical chance. The sheer mechanical forces needed to actually manipulate the sun's magnetic structure, well, they can't reasonably come from such a relatively tiny ice ball.
Okay, I accept the foundational physics, regarding the magnetic drivers of CMEs. That's solid. But I think your reliance on the tiny comet argument maybe fails to fully account for two crucial factors here: the speed of that mass injection and the fundamental nature of the interstellar material itself.
I'm sorry, but I just don't buy that the physical mechanism is entirely immune to any external perturbation, even a small one. Let me tell you why.
Okay.
When researchers looked at that famous 2011 event, the one that's often cited as proof of coincidence, they focused mostly on location, right? They determined the CME originated nowhere near where the comet actually disintegrated.
Right, I remember that analysis.
Yeah, but that analysis kind of relies on the assumption that any trigger has to be a localized impact, like right at the point of entry. But what if the injection acts more like a widespread, high-velocity shower of charged particles? The debris streaming off three eyelets, the stuff behaving like miniature steam vents in space, as they said it's moving fast. So if that debris cloud suddenly introduces a massive volume of charged hydrogen ions and water vapor, basically, foreign particles interacting with the native solar plasma right into a solar magnetic field line that's already unstable and storing massive amounts of energy, couldn't this dynamic influx provide maybe just a weak, non-localized trigger, enough to disrupt the delicate equilibrium of an already stressed magnetic loop? We might just be talking about a hair trigger situation here, not needing some huge impact force.
A hair trigger.
But the complexity, the sheer scale of the internal magnetic field structure is precisely why that kind of mechanism is, well, highly unlikely to work. The energy stored in that twisted solar magnetic field structure, the massive flux rope that ultimately becomes a CME, it's just orders of magnitude greater than any energy a comet, even an active one, could possibly introduce. Furthermore, CMEs are driven by the sudden release of that stored magnetic energy through a process called magnetic reconnection. To suggest that a small external injection of relatively cold, charged particles could somehow initiate this highly energetic, very specific magnetic rearrangement, the actual snapping and reconnecting of field lines, it's really asking a lot of physics.
But we don't fully understand reconnection trigger mechanisms.
If that mechanism were viable, though, wouldn't we expect to see a much higher correlation? With the literally hundreds of comets SOHO has spotted diving into the sun over the decades, yet the experts have confirmed time and again the vast majority of these sun-diving comets are not followed by CMEs. If the solar field were really so susceptible to some external hair trigger perturbation, we'd see far more, false alarms caused by just run-of-the-mill sun grazers. The very fact that the correlations are statistically rare kind of illustrates that the two events are independent phenomena that just occasionally happen to overlap in time.
Okay, that's historical analysis. I grant you, it holds significant weight for standard, native comets. I absolutely see that. But my core point remains that we cannot use that data from those comets to definitively exclude the possibilities of three outlets influencing the solar environment. This comet is the exception. It's not the rule here.
How so? Beyond the volatility?
Well, consider the distinct chemical signature of this interstellar object. We have near-infrared observations suggesting its coma contains chunks of volatile ice, maybe different kinds than we typically see. If this material has been preserved, potentially, in conditions fundamentally different from our solar system for like 4 billion years, it might interact with the solar wind plasma and the magnetic environment in ways that a standard, smaller, native ice body simply doesn't. The magnitude of the mass loss might be comparable in some cases, sure, but the type of charged particle influx could be unique. And we have this amazing opportunity to study this unique interaction precisely now, while it's close to the sun. We can't just rely solely on observations from less volatile objects that don't share the same, material history.
Okay, you're emphasizing the difference in composition, I get that. But you might be overlooking the consistency in the behavior of the CME mechanism itself. Regardless of whether the injected matter is 4 billion years old or, 400 years old, it still has to obey the fundamental laws of electromagnetism. The CME mechanism, it's an internal instability. It's a consequence of the internal balance of forces within the sun: magnetic tension, gas pressure, gravity. It's really not dependent on some external influence to kick it off. Think of it maybe like a dam breaking, okay? The structural integrity of the dam itself, the internal stresses building up, that dictates when it fails. A butterfly landing on the dam, representing the comet, it doesn't cause the rupture, even if that butterfly is exceptionally old or has, strange coloration.
Okay, the butterfly analogy.
The rupture happens because the internal stress exceeded the capacity of the material, right? The internal magnetic forces operating in the solar atmosphere are just so immensely powerful that any external input from a relatively small comet is, mathematically speaking, pretty insignificant to the overall energy budget involved in launching a CME.
I accept the dam metaphor, okay, but perhaps the butterfly analogy's a bit misleading here. We aren't talking about a butterfly just landing gently. We're potentially talking about a significant, unexpected injection of mass that is temporarily changing the local plasma density and maybe the magnetic resistivity right near an already unstable structure. If a magnetic loop is right on the verge of reconnecting, the process that actually releases the CME, we know it requires the local plasma to become more resistive somehow. So, could the sudden introduction of these high-velocity, highly charged particles from a unique interstellar source subtly alter that local resistivity just enough to tip the balance? I just think we haven't modeled the interaction of specifically interstellar cometary plasma with solar flux ropes rigorously enough to definitively rule it out, especially not with the kind of sensitivity we have in our observations today. Okay, let's pause there for a second. If you're finding this debate about comets and solar flares interesting, do us a favor and hit that like button.
Yeah, and subscribe if you want more deep dives into these kinds of complex scientific puzzles. We appreciate the support. All right, so you're talking about modeling future interactions, and that's a compelling avenue for future research, absolutely. But have you considered that the current activity level itself strongly reinforces the coincidence model, and that maybe diminishes the urgency to hypothesize these external triggers?
How do you mean?
Well, let's look at the context right now. The sun is currently in a highly active phase. We're near the peak of solar cycle 25, actually. And it's regularly producing, well, maybe not quite a dozen, but certainly several CMEs per day on active days. When the background frequency of CMEs is that high, it becomes statistically, well, almost surprising if one didn't happen around the same time as a highly publicized comet plunge just by chance alone. You see?
The base rate is high.
Exactly. We are just prone to observation bias here. We remember the dramatic convergence. Oh, look, the comet and the solar eruption happened together. But we conveniently forget that countless times a similar comet plunges without any solar follow-up. And conversely, we forget the hundreds, thousands of CMEs that erupt daily or weekly without any sun grazer anywhere nearby. This high frequency of CMEs provides the statistical noise that makes it really hard to pick out a true cause and effect signal, if one even exists. Until we have a testable, confirmed physical mechanism for this external perturbation you're suggesting, the most parsimonious explanation, the simplest one, remains statistical overlap.
Well, while I definitely acknowledge the statistical bias, the human tendency to see patterns where maybe none exist, We also have to maximize the research opportunity that this current environment presents. If the sun is in a highly active phase, producing lots of CMEs, and therefore presumably many near-hair trigger magnetic loops, then aren't we seeing the maximum potential right now for a subtle external influence to actually be tested?
Potentially more chances for coincidence, too, though.
Maybe. But if we restrict our analysis only to data collected during quiet solar periods, when CMAs are infrequent, we might completely miss the window where the sun could be, theoretically, most susceptible to these external tipping points. Right now, we have multiple comets approaching simultaneously. C2025K1 Atlas heading towards perihelion. We saw Comet Lemmon's tail get torn by the solar wind recently, and we have these incredibly close observations of 3 Atlas by the Mars orbiters. We just have this unprecedented temporal and spatial proximity of events. This density of simultaneous phenomena, I think, means we should absolutely maximize our research efforts now to try and identify any subtle connection that might have been hidden below previous detection thresholds. We shouldn't just rely solely on past data, which often used, frankly, less sensitive instruments.
You're essentially proposing, though, that if the solar atmosphere is already highly stressed, the fundamental rules of physics somehow change to allow a much smaller trigger to have an effect. That feels like a logical leap to me. The high frequency of CMEs during an active cycle doesn't necessarily make the system more susceptible to external perturbation in the way you mean. It just means the internal magnetic forces are regularly overcoming the stabilizing forces, which is exactly what we expect during an active solar cycle.
It's about sensitivity, not changing rules.
The CME mechanism is robust. It's internal, it's magnetic, it's just not dependent on external triggers from meter-sized or even kilometer-sized icy objects, however exotic they might be. Even if 3I Atlas injects some unique stream of particles, the magnitude of that input relative to the colossal energy already stored in those magnetic flux ropes is simply too small to matter fundamentally. Look, the solar system is continually bombarded by micrometeorites, dust, all sorts of space debris. A comet is just a larger, more visible piece of, well, astronomical littering in a sense. If the sun were this easily triggered by external bits, we'd see constant, chaotic CMEs, not a relatively predictable pattern tied to the solar magnetic field reversal cycle. We really have to stick to the known physics here.
Okay, so ultimately, this disagreement really rests on whether the unique properties of this interstellar comet 3I Atlas provide enough of a deviation from the norm to warrant proposing or at least seriously investigating a non-standard triggering mechanism.
Pretty much, yes. Is it special enough to break the rules?
Well, while we absolutely acknowledge that magnetic forces are the primary, the foundational drivers of CMEs, no argument there, the highly volatile and uniquely composed nature of the interstellar comet 3 Atlas, combined with the extreme close approach trajectory of C2025K1 Atlas, it suggests to me that the possibility of some kind of non-conventional influence on the solar environment shouldn't be definitively closed off just yet. The injection of massive amounts of unique, high-velocity charged particles into a highly energized system, it just presents an exceptional case. And I think it warrants further modeling going beyond just relying solely on historical sungrazer data from, standard comets.
And I remain unconvinced by that line of reasoning because, well, the foundational physics of CMEs remains resolutely internal and magnetic. And there's still no known mechanism, even considering the exotic nature of 3A Atlas, that allows a relatively tiny, icy object to initiate such a powerful, large-scale solar event. The available data, including all that extensive historical analysis of sungrazers versus CMEs, it overwhelmingly supports the conclusion of mere statistical coincidence, especially, as I said, when the sun is near the peak activity of its solar cycle. We really must adhere to the known tested physics until a viable, energetically plausible mechanism can actually be proposed and, crucially, verified.
So both perspectives here, I think, they demonstrate the sheer complexity of studying these transient events in astronomy. Timing, observation, scale, they're everything. And the debate clearly remains open, at least in some corners of the scientific community. There's always more to explore within the data, within the material.
Absolutely. It's what makes it fascinating.
Thank you for listening to Two Beans in a Pod. If you appreciated this deep dive into cometary physics and solar storms, please do hit that like button and subscribe for more intellectually rigorous exchanges like this one.
Thanks for tuning in.
Thank you for listening to Two Beans at a Pod. If you are interested in the book, please order it from the link below.